Можно дальше ничего не рассказывать. Знаете, это же такое время, что я спросил.
Dear colleagues and friends, today we start our end day of our conference, not global end day, only local, because tomorrow we can continue our conference outside of university. That's why I hope that will be a very interesting day for communication with each other. And today I want to introduce the third invite speakers of our conference. It's a very famous scholar in Ukraine, Alexander Adolfovich Letichevsky. It's academic, National Academy of Ukraine, which present Institute of Cybernetics from Kiev, and he present report about general theory, interaction of cognitive theory. Am I right or no?
And
cognitive architecture. Sorry. That's why I give what you. If you want,
I hope I shall speak loudly. Is my voice here?
No, it's better. Yes.
Okay. Well, good morning, ladies and gentlemen. Today we have an excellent lecture of Professor Pratt, who told us about the contemporary technologies in learning. And the next day we heard an excellent report of Professor Matske, who told us about the technologies in everyday life, in the world we live in. Now we shall discuss some problems connected with human mind. Last time this topic is very actively studied, and it is a great challenge creating a real-life computational equivalent of the human mind. It started many years ago, in 1956, maybe, and continues now at no. At Future 2045, and the goal of this program is to present to humanity immortality. Very ambitious program. I don't believe that it will be done, but very active, very large activity, and many famous specialists in artificial intelligence, psychology, cognitive science, neuroscience, and so on take part in this program. So there are two main approaches to modeling human mind. One approach is as now called, now, re-engineering of human brains. Engineers and neuroscientists studied human brain. They have a very large success in this. This is another level after biotechnologies which are only used. And they hope to make a model of human brain on using mainly artificial neural nets. Okay. The next approach, which is much closer to artificial intelligence, is synthesizing cognitive architecture using computer science, cognitive science, neuroscience, and maybe this is called BICA, biologically inspired cognitive architectures. There is society, BICA society, which collected many cognitive architectures. The most old is SOAR architecture, which is successor of early artificial intelligence, GPS, general solver, ARC, Clarion, EPIC, and so on, so on. They make very nice classification of these architectures, study the features of the necessary features of these architectures. You can find it on the internet. Here is a part of lists of these features. My talk is about the approach to cognitive architectures based on the theory of interaction. So the first part of my lecture is about general theory of interactions. Not all, but one approach which we are developing more than 10 years. Yes. What are the models of interaction? Mathematical models of interactions. There are several kinds of these models. Network models, which started from neural networks, and automata networks, battery nets, very famous, data flow diagram, and many other the models of parallel computing, and many other network models. More abstract are calculi, CCS, calculator communication system, CSP, communicating sequential processes. First is connected with the name of Milner, second with Hoare, 24, pi calculus, also Milner, mobile and bioambience, Italian, sorry, I forgot the name. He was a student of Milner. Developing Milner's school. Algebraic models, algebra of communicated processes, co-algebraic, very abstract on the category theory, in terms of category theory, the co-algebras. I'm not sure that it is widely known, but some very interesting people worked on it. My approach, I call functional approach. Instead of calculus or identities of algebra, I use the definitions of continuous functions. And this model was developed in I can go to the next slide because I shall return to this explanation. Now I start from basic principles of insertion modeling paradigm, which is the same as the model of interaction of agents and environments. The principles are, I tried to make them understandable on the level of human intuition, not mathematics. The world is an hierarchy of environments and agents inserted in it. Our environment now is our conference, and we are agents inserted into this conference.
Work as well.
Yes.
Me too.
Oh. And this conference also can be considered as agent, and it is inserted into higher level environment, which is called the scientific conferences of the world. Second principle, environments and agents are entities evolving in time. It is understandable. We have states and we change these states in time. Insertion of agent into environment changes the behavior of this environment. I hope that the influence of our conference to higher level environmental scientific conferences of the whole world will be visible, observable. Then, environment as agent can be inserted into a higher level environment. I talked about this. In multi-level environments, agents can move from one environment to another. The mostly important thing when agent is moving from another environment, this environment must understand this agent, because otherwise it will not be observable in this environment. And the sixth principle, which is the mostly important for cognitive architectures, is that agents and environments can model another agents and environments on different levels of abstractions. We do not know what is the world where we live, but we know a model of this world constructed by our mind during our life. So the models of mind must have this property, this feature. Insertion modeling is mathematical theory, first of all, and second, it is application theory. Sorry. Well, the theory of interaction of agents in environments was invented in 1996 by me and David Gilbert. At that time he was in City University of London. Society of Mind, the famous book Minsky. See, he also considered the hierarchy of agents and agencies It is not formal, but very interesting from the point of view of construction. Cognitive architectures. Mobile ambience. Luca Cardelli. Oh, this is the name which I couldn't remind. Yes? Are you listening?
Because as I see here, lose motivation and lose view.
Okay. So let's consider the next principle. Environments and agents are entities evolving in time. This is very simple. Many people select differential equations. I prefer level transition system. Abstract notion. The main property of this notion is that it separates the internal structure and observable part. Here is the example, simple example of transition system: states, actions, and transitions, and leveling of transitions and actions. The behavior of this simple transition system can be expressed by as an algebraic expression in behavior algebra expression. This is a very simple algebra. Two main operations: prefixing, and non-deterministic choice, and labeling. This is the constant successful termination and undefined behavior or approximation. In using expressions of behavior algebra, we can define only finite behaviors, but infinite behaviors can be defined by means of system of equations in behavior algebra. This is the main construction. And third principle's insertion of agent into environments changes the behavior of the environment. This is formalized by using the function, insertion function. It is very like to transitions in automata. Behavior of agent is the second argument. The first argument is the state for behavior. Usually we identify behavior and state. And this is a function. After insertion one agent, the state of environment changes and behavior changes, of course. And environment is ready for insertion of other agents. So we can write such expressions, algebraic expressions, and consider more rich algebra with insertion function as operation. Of course, behavior of agents define the transformation of environment. And we can, there was mentioned that states of agents are considered up to some equivalence, and there are two main equivalences by similarity, and trace equivalence is here we can obtain new equivalence, the equivalence of agents with respect to given environment. two agents are equivalent if they transform environment in the same way. For environments as an agents can be inserted into a higher level environment. This operation we can consider several environments and so on. Traditional approach is calculus and algebra, two theory of interactions. Our functional approach widened the possibilities to define insertion function and other continuous function over behaviors. Recursive definition, rewriting rules, SOS definitions for nodes, algorithms, any algorithm can be used. It must define only continuous function. And what is continuous intuitively is very easy. Behavior is an infinite tree, and to compute continuous function, you must use some finite prefix of this behavior. This is simple. High principle moving from one environment to another is illustrated by these pictures. It is internal environment, external environment, and agent moves up, moves down, or moves to another environment. And this movement is not necessarily physical, because the state of agent may have no time or special characteristics where it is. But of course, the special case is physical moving from one place to another. But when I'm now in the environment of this conference, I take my phone and call my wife, and I'm in environment of my family. I don't change my place. So it can be it can have different semantics. Attribute environments, of course. This is mostly important. This is the next level of abstraction. The first level of abstraction, equations and algebra of behavior algebra without details. What are actions? What are transitions and so on. But if we go closer to application, we introduce attributes environment. So the state of this environment is the mapping from the set of attributes. Attributes can be simple or functional also. And each attribute has type and domain, and also you can consider this environment as an object in terms of object, but not necessary. And when we have attributes, symbols, attributes, we can speak about these attributes. So we can consider the symbolic attribute environment, and where the state of environment is a formula of some logical, mostly first order predicate calculus. If you want fuzzy or temporal logic and other things, everything can be embedded into first order logic. And So this state, where is the state of environment, the canon, and states of legends can be considered also as formula of such. Now we can consider different levels of abstraction, because formula covers, in a natural way, covers the set of concrete states, models of this formula in logic terms. And one symbolic, one formula can cover a set of formula from which it is a consequence. It is very important from the point of view of cognitive architectures, because we never remember in our memory, never fixed all details of the picture which some details, yes. I know this this person is known to me, this person is known, this. Who are others? I don't remember. So, the unit of my memory is not concrete state, but some formula which describes the property which printed in my mind. Insertion function for symbolic adequate environments. This is a very important way to define the insertion function by means of local description. It is very like to Howard triples, reductions in artificial intelligence, frames transformation, and so on, so on. Simple conditional state. If the state of environment satisfies the condition, precondition alpha, then some process can be started, and when it finishes, the postcondition must be true. There's some conditional rule which can depend on parameters, and the set of such local descriptions define some set of define transition system, and when these conditions contain the information about environment and inserted agents, then it describes environment with inserted agents. Local description is a unit of model-based knowledge in insertion modeling system. I shall tell later about it, and cognitive architecture. And how implement these models, how make them right. For this we use the notion of insertion machines, which is an environment for simulating and insertion models. There are two kinds of machines, real-time machines and analytical insertion machines. Real-time, both kinds of machines investigate the behavior tree. The behavior tree of model, including, of course, inputs at the moment when we speak about real-time insertion machine. And there are two main parts: real-time for analytical model driver, in model description. In the first case, insertion machine produces behavior. In the second, it generates the traces of model description to get some knowledge about this model. This is the description of insertion machine in detail. I shall not discuss the details, but this picture shows the place of insertion machine in some cognitive architecture, in terms of cognitive architecture. Analytical machine produces traces using classical backtrack strategies, of course with some heuristics and everything which is needed, and generate traces which are written to episodic memory, the memory which contains episodes. We remember many episodes of our life, maybe with some details, so they are symbolic models of scenario which was in our life. Working memory, it's also from psychology. It is the state or some region of the state to make decisions. And all this is embedded, inserted into hierarchy of models which we call models. This is the architecture of insertion modeling system. It is the second system which was developed on the base of insertion modeling. I'm glad to tell that this system was developed in collaboration with Kherson University. Here is sitting one of the main developers, Vadim. Our first application was a system of VRS. It's called VRS, verification of requirement specification, which was developed more than 10 years ago for Motorola company, and now it is developing further by another company of the United States, and also we cooperate with them. The architectures of IMS is rather complex. At the bottom of this pyramid is C++ and other systems which we now learn how to integrate different systems, because we cannot in our small group, small team, to develop good cognitive architecture. But if we use everything which is open in the open world, for example, Z3 is a very good prover of Microsoft, and it can be used for research goals. It is already used by us. Plan C is the library of the main library of the name which can which is supported the language Aplan, algebraic programming language. It has a long history. You can read this history in the site. AP system. AP system is the one word. APS is algebraic programming system, and AMS development of this way. ICAR is insertion cognitive architecture, which is under developing now. Only the first steps are done. And why we started to do this? Because after studying what are cognitive architectures, we discovered that everything which is in SOR, ACTAR, other system is already in our system. Is already in our system because the insertion modeling is rather general system which supports many things which are needed for cognitive architectures. Cognitive architectures, I don't remember if I said that cognitive architectures are considered from 2 points of view. Sometimes cognitive architectures is identified with intellectual agent. Sometimes it is environment for the development of intellectual agents. IMS is such an environment. And this is intellectual agent, ICAR, which is under development of this architecture. Self-level. This is the higher level. Self-ego. Near this central is conscious emotions, and the main is evaluation of success. And also self-level made the control of all subsystems. System control. Here is the general definition. What is insertion cognitive architecture in this context? Insertion cognitive architecture is the insertion machine, this exact meaning, that conscious of self, understand self, as a center of evaluating the success of its behavior and tends to repeatedly achieve maximum success. And what is conscious of? It is monitoring of all internal system, distinguishes, this is the main important property, which is not easy for human. The distinction between internal and external environment. It's only on edges can be distinguished. But it is very simple in computer systems. Activity level include goal selection, planning, implementation of a plan, sub-goals, plan correction, usage of heuristic, and collecting experience. And use this experience, the home experience. Real-time activity and the analysis of past. This is activity level. Many useful things was made in robotics, which can be useful. Interaction with external environment, it is symbolic and shapes. Visual shapes. And also performing actions. This part, interaction with the external environment. Very important and very difficult for neuroscientists especially is language. From our point of view, the language for communicating is a meta-language for the language of our internal models. Our internal models are dynamic. And when we speak tell something, of course we speak about the models, our internal models, and how to do this. It is really difficult. A Russian poet Tutors said a phrase which изреченная мысль есть ложь. The thought which we spoken out is false. Why? Because it cannot describe exactly, in many cases, in many difficult cases, all our feeling, emotions, and also which is a context for this thought. Memory. Neuroscientists also do not know what is memory. Episodic memory, especially. Working memory, episodic semantic memory is ontologies. Many people here discuss about ontologies. It is very important. The main memory is the base of insertion machine, having different level of abstraction. Jeff Hawkins recently developed a theory of human memory, engineering, the Palm computers. Very interesting theory, but it is difficult to understand this theory. His book on intellect is much more understandable than the theory of human memory. I have no time to tell about this theory, but it is really interesting. I think that it will influence to neuroscientists also. Concurrency, of course, in the brain, everything is concurrent. And this is a problem to model concurrency. But, of course, maybe self-level is sequential. I cannot do everything at the same moment. I think even Caesar, when he did several things concurrently, he actually do something what do sequential control unit of computer, which is switching from different branches. But at each moment of time, he make only one. Others are on different level of feeling. From conscious, which observe ourselves, to deep subconsciousness. It's very interesting problem which must be discussed. That is all. I will have 10 minutes for questions.
Any questions? Please, questions. Please.
You talked about that in your insertion machine
Yes.
system, there is a possibility to
Speak up, please.
to enter the agent into the environment, and the agent will influence the environment, right? It's one of the main properties of the Glushkov. How do you think that you have the environment when the agent tries to insert itself with the purpose to destroy the environment?
To what?
Is it possible to destroy?
To destroy. Oh, it is good example.
To control or just to prevent from such?
It is a good example. Yes. Recently, me and my student write a program for VRS system. The security protocol can it be corrupted by intruder, and it is the terminology of insertion modeling is very good for this problem, and we develop a special environment which can model the environment, multi-agent environment, where there can be intruder. And the model driver of this environment analyze the behavior of this system and find if intruder can make some bad things. Please.
Thank you. I have a few questions. My first question is there a distinction between environment and context?
These questions I was asked many times, because insertion is a term which is used to insertion of some part of text into some context. Yes, of course, in some sense, the state of environment is a context, but it is changing, and we consider the behaviors, we consider the function, behavior of context and behavior of inserted agent, and this produce new behavior. So it is more complex than.
Is it fair to say that an environment is possibly a collection of contexts?
Yes, of course. You can model
as a collection of
context as a collection of context, which are the states of environment.
Right.
The main difference of agent and environment is in what agent observe and what environment observe. Agent observe only that things which is allowed by environment. Environment is better to say not about context but about the rules of world. Environment defines the rules of world, and agent only perform this
Thank you. Do I have time to continue with a couple of questions? Just basic fundamental questions. Thank you. The second question is, you talk about insertion, which is fundamental. Is it, I mean, you're modeling like a hierarchy, one included in the other. Is it a total containment? Is the extension monatomic?
Yes, extension insertion is monotonic.
It has to be.
Yes, monotonic because insertion function is continuous.
Exactly. Okay, that answers your question. My final observation is just one question. In the last transparency, you talk about transitions.
Yes.
Especially from unconscious to self. So my question is, because with respect to the languages that you described on interactions, it's all observable situations. But unconscious is something that is not observable. How do you make it observable in order that you can project a transition on it?
Observability is a main property of transition system.
Yes, but in your unconscious.
And when conscious is something around the self. Something around the self. There are agents around the self. And when some action is some message from self to agents which surround, it can be put deeper and deeper, and the environment when is the task generated by this message is not observable.
Right. It's not observable. Thank you.
More questions? Thank you. Dear colleagues, tutorials will start at 10:30 here. So now we can find a cup of tea or coffee behind this door.
Давид, я могу это сообразить сейчас? На среду, я не знаю, искать. Это тоже на 3 часа. Я даже не знаю. Потому что это надо, я, честно говоря, не знаю, что вы меня входите.
We can continue our work. Tomorrow tutorial is ontology alignment and applications by Vadim Ermolayev with assistance Maxim Davidovsky.
Okay, thank you very much indeed for introducing us. 2 things to mention before. The tutorial will be hopefully 90 minutes. I'll do my best to stick to the time schedule. Secondly, I just discovered that my business cards have become very popular, so there are some in a pile here on the table. Please rush to make it even more messy. I'm going to tell you several basic and perhaps more interesting, more advanced things in a rapidly developing and I would say hyper discipline, which is ontology alignment. As far as the conference is closely related to real-world applications in the industry, we planned a third part of this tutorial to map how these approaches, technologies could be demanded by, could be used by different industries. And this is why I'm saying hopefully 90 minutes. So, perhaps we will do it in a flexible manner. Speaking about the constituents of the materials related to this tutorial, I need to mention several of them. The tutorial itself have been developed in my group in Zaporizhzhya National University at the Department of Information Technologies we all belong to. A theoretical framework is a little bit outdated. We have developed it in our former project and it in 2005. But since that, we did a lot in practically implementing it and trying on both academic and industrial ontologies. For that, Maxim, sitting there, please stand up. As a part of his PhD project, has developed several software tools, both for industries and for academic research. Today, we will demonstrate some tools which have been developed as an open source solutions for academic research. This is a structural difference discovery engine. This is an instance migration engine developed using the Eclipse framework. For supporting this tutorial, we also offer a thing which is well aligned with what Gary told us the day before yesterday. We're trying to put people in virtual groups to boost up their learning performance. For that, we use semantic media wiki. Media because we may use different medias. Wiki is for social crowd gathering, crowdsourcing. And semantic means that we inject a lot of semantics in this wiki, and therefore it is also well aligned with the major topic of this tutorial. Ontologies mean semantics. Questions and answers are supported using one more tiny tool, which is popping up in the wiki and allows you to type in or voice in questions to all those who are at the same page. This is exactly the mechanism to form virtual groups here. And this is not ours. This is the development of our Slovenian colleagues. This is, well, majorly a German effort to develop this. So the plan of this tutorial is pretty straightforward, and these as follows. In part 1, I will try to motivate you and explain why it's so interesting and enlightening and perhaps necessary to study ontology alignment. For that, I will tell you a little bit what is an ontology and what is ontology alignment. I will also try explaining you why the technology for that is needed both for education, research and industrial applications, and I will also tell you what is the structural landscape or problematics in this field. What are different problems and sub-problems, and how could you classify those problems using different dimensions. In part 2, we'll do more practical things. We'll pick up a very simple teaching example of 2 ontologies and show you how it's aligned using as an example 1 sub-problem, an instance migration problem. I will tell you a little bit later, which is exactly the topic of Maxim's PhD project. And hopefully, if time allows, we'll go to part 3, where I plan to show you why ontology alignment may be useful in one industrial application category, in distributed information retrieval, which is more and more broadly demanded and used by different industries today. For support and questions, as already announced, we will use this A-bar wiki we have developed for the previous instance of this tutorial, given last year at WIP's 12 conference. And this is the wiki, by the way, on the second screen. So those of you who are online may type in the URL, go in there, follow the tutorial, and hopefully, if the bandwidth allows, pose questions to all those who are at the same page. You'll see those guys sitting at the same page here when the LiveNet Live pops up here. You know, so different icons for different humans attending the same page there. So questions and answers may be reacted by us in different manners. If there is something specific related to a particular page, I hope that Maxim will do his best and answer using this LiveNet Live or other interface. And if there is a general question, you are welcome to stop me at any time, stand up, ask a question, do whatever you like. It's an academic tutorial. So, the wiki is available permanently, so if you would like to go through the material a little bit later to refresh your minds, you may go there to this very persistent address and pose questions right there. There is a particular functionality provided also by Semantic Media Wiki stuff right there. If you're interested in details, either please ask or come up to us after the tutorial and we'll show you how it works. So, I'll start with a walkthrough problem and the workthrough example just to give you the key and the clue for the rest of the material. Ontology instance migration problem is a very interesting problem which arises quite often in the situations when your data, your information, your acquired knowledge is changing in time. For example, when a new version of an ontology schema is developed, which happens quite regularly in those enterprises who use semantic technologies, and we well know it from our industrial consulting experience with cadence design systems, for instance. We produced a new revision of an ontology in a period roughly of 3 to 6 months. Implemented major changes in the schema, but at the same time the individual assertions of the knowledge base which is collected using this schema is incrementally increasing. So after several years you find it out that you implement a major change in the schema, you risk quite seriously to lose a lot of background knowledge collected in your knowledge base because you cannot transmit it without a mistake. Another good example, which is also very interesting to for industrial applications, is the whole domain of software or information integration problems. We heard about that the day before yesterday from Gary. We heard about that yesterday from Wolf. And I believe we implicitly heard about that even today from Professor Letichevsky, who mentioned that agents living or inserted, sorry, I prefer situated, but inserted in different environments have to interact and they may definitely use different terminology for this interaction. So they have to understand each other, therefore align their knowledge representations. By the way, this very approach of using agents, aligning their knowledge representations, is used in our software tool. We'll show in the second part. So, well, schematically, the solution for an instance migration problem, which is actually taking the assertions from an older schema and putting these assertions transformed to a newer schema using transformation rules which are carrying this alignment semantics, and which are, well, XML based and quite formal, is done in two phases. First, we have to compute a structural difference between those two schemas. If you implemented a change in the schema, it is not necessarily that you have documented the change. And even if you have documented the change, you have to transform this documentation into the formal rules, understandable by a software program solution, to transform the instances and to migrate it to a newer schema. So here we compute the structural difference. Then these instance transformation rules are automatically generated. Then the rules are used by a different program to migrate instances, transforming them on the fly. And then we have to evaluate. If we are lucky and we know what would be a result, for example, we have a golden standard A box for a newer schema, which rarely happens but may happen in artificial scenarios. Then we just compare the result of automated migration to what is the real target and fine-tune the solution. If not, we have to evaluate it using different methods, and we'll also show how it works in our practical solution. For that, this is a very brief and very short presentation of the schemas of our ontologies. We used two different ontologies which formalize the bibliographic domain. Just imagine two different agents. One is, like myself, a PC chair at a conference. Another one is my colleague sitting somewhere in Springer and having his own information system with his own rules for structuring data tokens which have to be put there if you put your proceedings to their information system. I'm using EasyChair. He is using Springer conferences. They are different. Believe me, I tried both. So the problem is that if you have a paper concept here, there could be a proceeding paper concept in the Springer system, and those two may have different properties, both data type properties and object properties, and they may have different cardinalities for object properties, and the configuration of those contexts also could be well different. So all those inconsistencies and mismatches have to be resolved in the process of constructing or discovering the structural difference between those two. This is the assertional part. I'm sorry that it's not well shown, but there was no other choice. The names are different. The content is also different for the assertions. So now I'll try, having that, now I'll try to give you the basic part of the material. I will first speak about the motivation to study the alignment a little bit deeper. I will then give you some denotations leading to a better understanding what is the ontology alignment. I will show you that the ontology alignment is the result of a process of ontology matching. And then I'll finish up this part with presenting you the classification of the problem domain here, showing you that, well, it could be well possible to consider the whole domain as one bold and generic ontology alignment problem, but using some practical considerations, it's much easier to pick up a sub-problem which is particularly relevant to your application problem and then solve it easier compared to the solution of a generic problem. So, to start motivating you to look in this domain, I would first like to cite Tom Gruber as one of the most visible figures in knowledge engineering, knowledge representation and reasoning, who wrote once that he found it critical to remember that every ontology is a treaty, a social agreement among people, and I would say also among agents, with some common motive in sharing this knowledge. So having a data scheme is fine, having a knowledge schema is fine, but until a community of people or artificial agents commit to this schema, is useless. Nobody will use this and nobody will add his individual assertions using this schema as a namespace. And the interpretations of different people looking at the same schema of knowledge representation are well different. This is a very good and topical example. Do you people recognize the face? Yeah, at least Gary. You too? Do you remember the name?
Marilyn Monroe.
Exactly. And those people sitting over there in row 20, do you recognize the face?
Yes.
Good. And now? Do you still recognize the same face from row 20? You see? Interpretations are subjective, interpretations are contextual, interpretations are, well, are changing in time. There is a good argument for me to say that the world is multifaceted and polysemic. Well, even in this very simple example, there is a piece of multisemicity as well. So at least this guy you see now is a male, and the girl you saw before is a female. That's a difference in semantics. Many different views or interpretations by different individuals or groups may exist concurrently and competitively, I would say. Those are reflected in different knowledge representations, formalizing the same problem domain. This is why I would like to refer you back to Tom Gruber, who said that each successful, that's what I'm adding, each successful ontology is a social treaty, bringing together a group of individuals committing to a same or very similar knowledge representation formalized in an ontology. So many things across those different and several facets and across subjects may complicate the problem. Several knowledge representations have necessarily or could have been necessarily harmonized or aligned, because otherwise those two agents sitting here at ICTERI as a program chair and sitting there as Springer as their program specialist would never talk using the same terminology. If we start discussing with Professor Letichevsky what an agent is, and if we do not align our understanding about insertionness or embeddedness in the environment, that will be a dead end. But perhaps we'll do it much quicker as the program solution because we're a little bit smarter. So, those representations could be informal, like that one. Those representations could be more formal, like those I showed before as fragments of UML diagrams. They could be even more formal, coded in ontology specification languages. So, we have to have an automated solution, especially if we strive for an industrial strength solution, to help people do those very challenging tasks. Align knowledge representations, allowing them to speak the same terminology, using the same assertions to solve their different tasks in distributed settings. So alignment is essentially a result of applying a set of formal transformation to a knowledge representation, both to schema and individuals. I mean, in a generic, in a broad sense. Alignment allows interpreting knowledge that is external to the interpreter. In the same way, the interpreter views his own knowledge schema and assertions. So it makes those differences between me and the guy Springer transparent and not noticeable. For example, for those two fragments which are identified like Biblia 2 and Biblia 1, a publisher, the guy Springer, using the aligned variant of this knowledge may seamlessly import the assertions about the accepted papers to this knowledge base. And a conference organizer, for example myself or Alexander Spivakovsky, could get publishers' information about the publication constraints like page limits, and this is why they have a common motive in sharing. This is why there is a chance that they will both commit to the alignment to satisfy this common motive in sharing this knowledge. So, as you may have realized already, many kinds of important applications require such a solution or such technology. Do you follow me? Yeah, if you may have noticed, he is showing you the pages in the wiki which are relevant to those things I'm speaking about. So, speaking about the basics, I feel that it might be necessary to give you some basic definitions before starting showing any fancy stuff further on. So I will tell you what an ontology means, what is an ontology schema, what is an assertional part, what is a mapping, what is an ontology matching process, and based on that I will define what is the result of an ontology matching process, ontology alignment. Then I'll give you a short overview of the classification of ontology alignment problems and spend a little bit more time and a little bit more formality using a little bit more mathematical symbols for showing you what is a walkthrough problem, an ontology instance migration problem. So the basic definitions are as follows. I will be following a well-known textbook written by Jerome Busenard and Paul Schleichwolf, which is ontology matching, it's Springer, it's 207, and well, an ontology in fact is a tuple which is that ugly until you read all the rest below this line. C here is the set of concepts like proceeding paper, PC member, author, volume, and so on. P is the set of properties, both object and data type properties, like author is the author of proceedings paper. A proceeding paper has the title, start page and end page. I is the set of individual assertions. Like for the proceedings of ICTERI 2013, the title will be the 9th International Conference on, and so on. T is the set of data types. For example, for the title of the proceedings paper, it would be a string. For the starting page, it may well be not a string but a number, an integer. V is the set of values. The exact value of the starting page for this tutorial paper in the conference proceedings of this year. And those are more fancy things which allow us to build formal and tractable constructs. For example, hierarchies in ontologies. For example, this relationship says that one concept subsumes to the other concept. This relationship says that they are mutually disjoint, and so on and so forth. I would not like to go into details here, because otherwise we will be behind the schedule. So, an ontology comprises, as you may have guessed already, its schema, the description of classes, concepts, the description of properties, the description of data types, and the description of some other axioms which may be constraints on data types, constraints on values for this particular property, and so on and so forth. An ontology also comprises the set of individual assertions, which is in fact the knowledge base, which is in fact the knowledge people use in their everyday work, and which is in fact structured using the schema. All the axioms which we have defined in the schema are applied to the individual assertions. In turn, individual assertions are attributed to particular parts of the schema. For example, there would be an individual assertion attributed to a proceeding paper. For example, the proceedings of the 9th International Conference, ICTERI 2013. And there would be another individual assertion attributed to a PC member like myself. And mapping, or mapping rule, is a tuple like that, which allows us to, in fact, compare two different things taken from two different fragments, perhaps from two different ontology schemas, in order to discover a similarity or a difference between them. E and E prime are the elements of those different ontologies. They may be concepts, properties, individuals, data types, and values. R is a set of mapping relations. For example, equivalent. And finally, and perhaps the most interesting is M, which is a confidence value. To how much are you confident that this paper is equivalent to proceedings paper? This is I'm pretty confident in, and this is why I put one here. This M is a normalized value and takes values from the interval between 0 and 1 inclusively. A more complex mapping with a different sort of relationship here may be used when you want to implement alignment. For example, when you want to migrate instances or individuals from one ontology O to another ontology O prime, or 101 to O2. We'll show you later how it works. And here, the relationship R is migrate. And we are pretty confident that this one should be migrated to that one, and this is why we put one here. In a language which is used by Maxim's software, the same line, which could be well readable here, reads like that. Well, it's an XML stuff, and those of you who are familiar with XML can definitely see the equivalence between the alpha line and this fragment of XML code. Any questions here? No. Ontology matching is the process of discovering the mappings, those mapping rules between the elements E and E prime taken from different ontologies, the source ontology L and the target ontology O prime. So a generic ontology matching process is discover mappings, like here on this diagram. We have source ontology, we have a target ontology, we perhaps have some differences in their schemas and assertions, and we do this cloud whatever we understand by that cloud at the moment. And after this cloud is executed, we get a set of mappings, mapping rules, which have to be applied to the source to get the target, or if it's bidirectional, as I will explain later on, then we have to apply to the source to get the target and to the target to get the source. This is why in a generic setting both of them are gray here, because both of them may well receive changes. Ontology alignment is in fact those grays, those which are the results of applying mapping rules, those mappings, to either source or target, or both of them, to get the result. This leads us to looking at different kinds of ontology alignment problems. Because as you may have already guessed, the process may be unidirectional from source to target, or bidirectional in both directions. The process may involve only the schema for discover mappings, but also the schema and assertional part, and so on and so forth. So this leads me to the second subsection in this part, which is the classification of ontology alignment problems. This one you have seen already, defining the context E, which belongs to the source ontology O, and the context E prime, which belongs to the target ontology O prime. Ontology alignment problems will be classified using different facets, so different dimensions, as it's written on the slide. The first is span. How far the alignment propagates over your ontology. It may be complete, both schema and assertions. It may be structural, only schemas, and it may be only assertional. Only individuals of the ontologies are aligned. For example, ontology instance migration problem is an assertional problem. The next dimension is dynamicity. The setting for solving a problem may be static. That we subsume that both source and target ontologies do not change in time when the alignment is executed. And if we want to complicate this scenario, we may require that either one or both of them are changing, and that will be quite a task to implement the alignment correctly in these changing settings. One more dimension is direction. As I have already mentioned before, alignment or matching process may be bidirectional and unidirectional, only from source to target. And finally, the fourth dimension is the degree of distribution of your problem setting. Some problem settings operate as fully distributed, when there is no central referee ontology suggesting you or hinting you about possible bridges between the concept here and the concept here, property here and property here. And the other setting may use a central referee ontology for that, which eases a little bit in our lives. So by the span of aligned elements, ontology alignment problems are classified as complete, as I told you, structural, and assertional. With respect to dynamicity, they are classified as static or dynamic, and those are the diagrams. See, those two are changing. For example, if it's a structural alignment, or we look for structural difference only at this discovered mapping space, and the schemas change while we are looking for structural difference, there will be a complication to our task. By direction, the problems are classified as bidirectional when both change, source and target, and unidirectional when only a target changes. For example, this instance migration problem is a unidirectional problem, because we do not care about the changes in the source. We just take the source, transform it according to the set of the discovered mapping rules, and put into the target, so the target changes, and we don't care about the source. This is why unidirectional. And by the degree of distribution, as I already mentioned, there are scenarios when you have this central referee ontology used to provide additional evidence about structural similarities or differences or not, and then it's fully distributed setting like here. To add a little bit more, we may also discover, and will discover later on in the demonstration, that the problems could be solved either in one shot or iteratively. We'll show you in our demonstration that one-shot solution usually lacks a little bit of quality, and in terms of migrating instances, it misses a little bit of instances. This is why it may be required to do iterative refinement. That means that after applying mappings here, you have to evaluate somehow, and if you are not satisfied with the quality, with the number of migrated assertions in our case, for instance, you have to refine something and iterate. Do this migration once more. Okay. Now I'm going to explain the problem. Oops. Thank you. This is a very common thing you have already seen several times. We have a source ontology with a schema and an assertional part. We have a target ontology with a schema and assertional part. The schemas conceptualize the semantics of the same universe of discourse. For example, those two ontologies are in a similar problem domain. An ontology for a PC member and an ontology for a Springer worker. The universe is regarded as a collection of ground facts, which could be explicitly represented in the ontologies or not. Because any ontology is a model and is a simplification of the real world. Essentially, as I have already shown you in this good example with Merlin and Albert, OS, the source ontology, and OT are the interpretations by different groups of agents or people or actors which subsumes both. Those two may be considered identical if and only if, for each ground fact from the universe, the interpretation of this ground fact in a source ontology is equivalent to the interpretation of this ground fact in the target ontology for all. For example, either Merlin or Albert are identically perceived by all the people sitting here in the audience, irrespectively of the row number. Let us subsume that at some point in time, those interpretations are not identical. That means that there is a difference between OS and OT with respect to the given universe of discourse. And then I'm able to introduce an abstract metric of interpretation difference, which will make normalized. ID will be equal to 0 for identical OS and OT. ID will increase monothonically T1 with the increase of the number of such facts which are interpreted differently. and ID will be equal to 1 if and only if there is not even a single fact that is interpreted identically in those two. If you consider this very simple arithmetical expression 1 minus interpretational difference, you may further find out that it's very similar to a well-known balanced F measure, which we all know from the domain of information retrieval. And further on, we will use this balanced F measure for the overall evaluation of the semantic difference between different ontological contexts of the source and the target ontologies in our solution. OS and OT are structurally different if their schemas differ. Then a structural difference could be regarded as a transformation T, transforming a context from the schema of the source ontology to the corresponding context in the schema of the target ontology. And this T may be solved in the form of a set of nested transformation rules, which is exactly the approach we used in our implementation. The problem of minimizing this interpretational difference between two ontologies could be put algorithmically as follows. First, we have to take the individuals from IX. Then we have to transform them correspondingly to the structural difference discovered between OS and OT, and then we have to add those transformed individuals to IT. This is exactly the problem which we identify as ontology instance migration problem, and we use as a walkthrough for this tutorial. And according to our classification, it could be classified as assertional, static, unidirectional, and distributed. And this is the diagram for that. Theoretically, the ontology instance migration problem could be solved in one shot. But in practice, and we'll show you why, each of the subtasks here or here may result in the loss of the assertions because of different reasons I'll go into at the moment. So iterative refinement could yield results with a lower resulting interpretational difference measure. An iterative solution will develop a sequence of sources in the states to minimize the target interpretational difference in a way as shown here. So the interpretational difference in a state I, which is before state J, would be higher than the interpretational difference at state J. So this sequence is monothonically decreasing. And now we're going for a demonstration yet. For that, I will answer several questions from a hand group. So far we have answered the question, what is it? And now we're going to show you how it works to solve those whats. It's a little bit more advanced material. It's more focused on agent-based approaches for building ontology alignment because we use this agent-based approach in our solution. First, I will remind you what an agent is, though I'm allowed to make it very shortly thanks to Professor Letichevsky, who did it before. Then I will show a map of the research and development landscape in agent-based frameworks for ontology alignment. Then I will very shortly explain the approach algorithmically, and then we'll show the solution on the example which is in bibliographic domain. So, a software agent is a software entity for which the following main point is true. agents are autonomous, meaning they're capable of acting independently, exhibiting control over their internal state. So, an agent is a system capable of autonomous action in some environment. Whether inserted or situated, so far it's not that important. You may find, if you look around, you may find plenty of good examples of trivial, not very interesting agents. For example, if you look over there, or to the back of the room, you will see this air conditioning systems which use thermostats. They react to the changes in the environment, they measure temperature. And when the temperature goes down at a certain threshold, they switch themselves off. That's very simple, that's trivial, and therefore not very interesting. Another example, many of you are online and some of you are checking your emails, and some of you are desperately looking for an important email which you should have received by now already, but it's not yet here. So please check your trash box, or please check your spam box, because there are spam filters or email filtering robots or agents who do that for you, and you're making you not that happy. So an intelligent agent, which is a little bit more interesting than this trivial or non-interesting agent, is an agent is a computer system capable of, and I will stress it, a flexible autonomous action in some environment. And by flexibility, many different people, already mentioned by Professor Letichevsky today, who developed the abstract frameworks starting in the 80s of the previous century, mean that those have been reactive, those may be proactive, and perhaps if we especially consider our case, they have to be social, to come to a social commitment. So a reactive system is one that maintains an ongoing interaction with its environments and responds in a timely manner to the changes that occur in the environment. Those air conditioning systems are reactive. Unfortunately, nothing more, therefore not very interesting. Proactiveness equals to generating and attempting to achieve goals, not driven solely by reacting to events, but taking the initiative, recognizing opportunities. For example, if you put a grand goal ahead of you to finish up your PhD project in, I wanted to say 3 years, yeah, unrealistic, 5 years, then you may choose different pathways to reach this goal. And this is proactivity, because you are free to choose the most effective or productive pathway in your personal opinion. You too. So, this is a good example of proactivity. Requires goal-directed behavior, which is directed by goals set up in advance. One more aspect which characterizes skill and flexibility is the social ability. All things I told you about agents before were about individual agents, and now we are coming to groups when several agents interact with each other. So social ability means that an agent has to be able to do this interaction with other artificial agents, or perhaps with other human actors in some kind of agent communication language, which is formal. It has to be able to adjust its behavior according to social norms. And one more brilliant example of a non-social agent you may find on YouTube if you go and type in Scottish then elevator. It's a very, very short video, and you will see that a new speech recognition system, high-tech, installed by the Americans in an elevator in Glasgow, is not really social, because it cannot communicate and recognize the messages in an agent communication languages coming from human agents. Scottish guys. Yeah, one important aspect is cooperation. Recognizing messages. Found it? Want to put it on video on the screen? Yeah? After. In a coffee break, please. Are you crying already? Scottish elevator. Eleven. Did you see Gary? Not yet? I haven't. And delicious. Okay, I have to go further. As far as an agent is, and now we have a breakpoint with Professor Letichevsky. I would say as far as an agent is situated in the, situated in the environment, it has to have a perception function. It has to have to perceive something that happens in the environment and changes the environment and act accordingly. So minimally, it has to have a sort of a C function which characterizes the agent's ability to observe the environment and to detect something changing there. Whereas the act function represents both agent's decision process and the outcome of his decision. In our case, both discovering matching rules and the ontology alignment, acting in terms of implementing this matching rules. Output of the C function is a percept. A small piece of information, an information token extracted from the environment characterizing the change. Here. It maps the environment states to those information tokens. And the action here is not a function act which maps those percepts to a set of actions or sequences of the elements of those things. Having said that, I will just outline a very generic and a very abstract agent control loop here. First, it starts in some initial internal state. Then it observes the state of the environment here and generates a percept. Then the internal state of the agent is updated using this next function based on the analysis of the information token in the percept. And the action is selected by the agent from his portfolio of actions, and then the function act is performed. This is one iteration of the cycle. Then it goes to looking and perceiving the environment. Okay, that's distracting people from that. Make it louder. Scotland, freedom, eh? Not yet? Okay, 11. We have to put it on, yeah, publicly. Later on. Okay, now we're going to give a little bit more theoretical foundations for agent-based ontology alignment. Okay, I'll wait for a second. Close this down, please. Okay. As far as our software implements an agent-based approach to those bits which perceive the environment and interactions of those processes. We have to slightly modify the setting for a generic ontology alignment problem. So we have to inject agents in it. What we do? We look closer at a Discover Mappings cloud here, and we look closer to Apply Mappings cloud here. Now we see that this ontology is either wrapped or in some other use cases owned by particular agents which are responsible for this piece of knowledge representation. The target ontology is owned by a different agent. This is W if you can't read it, and this is W prime. Perhaps there is a central referee agent which owns this central referee ontology OR, And then they interact, socialize, and cooperate to discover mappings. Those discovered mappings, as you may notice here, may be well different for this and that. This is a generic setting which allows us to solve both uni- and bidirectional problems. For unidirectional problems, we'll use only one part of those sets of mappings. So, this approach, agent-based approach to solving ontology alignment problems, have found a substantial interest in the community and substantial attention in the literature. If you look here at the map, there are some points on the world map here in Britain, for example, here in Portugal, here in Barcelona, here in France, here in Germany, Netherlands and Belgium, here in Ukraine, and even here in the Southeastern Asia, the different theoretical framework and practical solutions for that. Mostly, I mean, in the mainstream, those theoretical frameworks are based on different flavors of negotiation technique based on exchanging arguments as the most natural and well-proven mechanisms for reaching agreements. Most widely used formalism is the Dunk's argumentation frameworks or its derivative, this point here. It sounds a little bit strange, but this guy has appeared to be a pioneer. The formalism we use in our software solution is negotiations on propositional substitutions. Those propositional substitutions are formed of propositions formed over semantic contexts, and those propositions are based on the use of a logical formalism known as tag theory. So algorithmically it works at a very high level of abstraction. It works as follows. We have those two things, OS and OT, a source ontology and a target ontology. First we have to choose a center of gravity to hint our agents where to start from. The heuristic here is that for a center of gravity you use two concepts or two classes which you as a human perceive by your backbone, for instance, as the most well-matching and the most complex among the rest. So if you find this center of gravity, you fit it into the agent system and they will do the rest. So they discover mappings for structural context by exchanging hypotheses, propositions, try the substitutions on those propositions over their own statements in their own ontologies, and they will be measuring how similar the propositions and the propositional substitutions are in terms of semantic similarity or several different metrics of semantic similarity, which is contextual, which is linguistic, and several others. And they will accept good propositions, probably in concession iterations, as it happens in negotiations. After an agreement on a context is reached, perhaps with concession, then we exclude the pair of central concepts in this context from the negotiation set and get the problem which is smaller in size, going to the next iteration until we get the whole set of mapping rules. This is an example. I'll skip it. And now we go for the demonstration. So the workflow for the demonstration and for the solution is as follows. We first use the structural difference discovery engine to discover structural changes. We then use structural difference discovery engine to automatically generate the mappings and the transformation rules. We then use the instance migration engine, another program here, to migrate the instances. We then manually analyze the instance migration log produced by this IMEs tab to find out if we are happy or not with the quality. And that, if not, and that will be the case, we'll go to the next iteration by refining the set of transformation rules and doing one more instance migration. Question? Yeah? You did. Okay. So, a few words about the ontologies. Both the source and the target have been picked up from. Oh, how much time do I have? Grigori? Yeah. How much time do I have? Half an hour. 20? Okay, thanks. No applications next. So, both of them are used by the Ontology Alignment Evaluation Initiative. It grew up as a pan-European initiative and that's a world initiative, putting together the software solutions for ontology alignment problems and providing a benchmark, a test bench set of ontologies to test the solutions and to compare the results. So we picked up 2 arbitrary small ontologies from the whole set. They have differences. Could be characterized as you may read from this very simple table. This is the number of axioms in total, including this, and that. Logical axioms, number of classes, number of object properties, data type properties, named individuals. You see, this guy has 57 individuals, while that one has only 1. And we have to migrate all those 57 from Biblia to INRI. Some of them are well named, some of the other are anonymous individuals. So it's not really possible to apply linguistic or textual metrics for the similarity judged by the names. This is to give you a hint of how do the class hierarchies of these 2 ontologies may look like. This is for what? Maxim?
This is for INRI ontology.
This is for INRI and this is for Biblia, right? May I have one more microphone here? So, now you take the floor and launch the ontology launcher. This is the solution for discover mappings, the first cloud, the upper cloud in this game.
So now we're starting our multi-agent system. It is implemented using J agent development environment. Here you can see our agents, agent 1 and agent 2. Agent 1 is responsible for Biblia ontology and the second agent is responsible for INRI.
Speak up, please. Louder.
Yeah, I try. Then we have to enter the start point class, the class that Vadim named that something like the center of gravity. And then we have to enter the threshold to cut our mappings according to this predefined threshold. Empirically, we determine that in most cases it should be the value circa 0.4. So we have our alignment in alignment format. You can see this here. And
this is the fragment inside the data. which is of particular interest and simple enough to be put in one slide and to show you the facts which may lead to casualties in terms of losing instances on the way of migration. So, we have chosen a center of gravity as Maxim showed. He also specified the similarity threshold. He also started this very simple multi-agent system comprising two agents, one responsible for source ontology, one responsible for target ontology. They did their mappings using this center of gravity and looking around, taking all the structural contexts into analysis, and finally they produced two kinds of the output. The first was the alignment format, the presentation of the structural difference between those two schemas for manual evaluation or for using some tools for visualizing and manually evaluating the step, and more important thing, the set of transformation rules here. So if you look at the whole set of the transformation rules, which has been very briefly shown by Maxim, you will see that the marcher has found those mappings and put those in a set, which are means that this is a reference mapping, a golden standard provided by the Ontology Alignment Evaluation Initiative, and M means that this is the mapping discovered by our matcher. What can we say is that all the mappings which are in the golden standard have been discovered by our matcher. We can also say, we have to say that it's not enough, because some of them have not been found. They were not in the reference matching rule set.
Vadim, sorry, may I interrupt you? Just a few words. This mapping, reference mapping contains only trivial mappings, one-to-one mapping, and they provided this mapping is actually something like the best result of the previous contest, the previous year, and so this alignment is not complete.
Okay. So, if we look at the fragment of the alignment format given on the Maxim's screen, we may see in a graphical representation, while analyzing it using a tool, that for this context in the Bibler ontology and for the corresponding context in the rear ontology, we found two concepts which have similarity over the threshold. But they're still different because it's not equal to 1. Okay. Now, if we look at the set of transformation rules suggested by the software solution, we will see that it suggests first to remove this object property, the relation between the reference and person list, and then to introduce a new one with a different name between the entry and person list. So, I won't go further here, but you may imagine that behaving such rudely with object properties in the source may cause casualties. You may lose something. If you drop this property, you may lose the connection of some individuals between individuals here, and those would not be properly migrated. And that is exactly the problem we have discovered during analyzing the migration over there, I believe. But first we have to start migration. Maxim.
Here you can see simple interface, deal with transformation rules, and in general with instance migration engine. So here we enter this transformation rules, and then we can execute migration. Our migration is finished. Here we can see the log. Here on the slide we have a snippet of source infos that is correspond to the presented quantities.
And if you please show the target box, the result, and you see that there is no assertions here. So we missed something. And now we may have a look what has been missed by analyzing the migration log, right? This is the fragment of the migration log on the screen. What can you see there, Maxim? Because I can't see it from here.
We can see that we lost an assertion, namely relation or object property named human creator.
So exactly that, because we have dropped this, we deleted this this object property that caused that we didn't create several individuals from here to the target. So this is why we decided to go to the next iteration and to refine the transformation rules using humans, experts in this domain. And those came out with non-trivial mappings, which means that those mappings you saw before were in the reference mapping set were trivial, and those are not that trivial. This is more general than, this is more specific than that, this is more general than that, and so on and so forth. This is one-to-many mapping, so a text may map to article, to a chapter, to a report, and so on. This is not that easy as it was in one-to-one mapping with the only one relationship equal to equivalence. So we modified the transformation rules manually using the same interface of the instance migration and engine to edit the rules. And after that, we started the second iteration of the migration. Sorry.
I already uploaded the part solution rules. Then we can do migration to the final solution. You can see all again. Here on the slide, we can see refined transformation rules. Namely, we substitute remove relation tag with the name relation that allows us not to lose assertions. And here is target equals fragment. As you can see, here we have author assertion that was lost from the previous iteration.
Yeah, you see, the problem may become even more difficult if the author lost there is an important person in the community, like Chris Simperan here. So we did our best to keep her in the community and migrated her to a target ontology. So as far as we have no time to application, I would say that if you go to a wiki, you may see some applications mentioned and described there. Both the one we planned for today, but I'm sorry we have no time for that, is distributed information retrieval and several other categories. So if you are interested, please go to the wiki, please look through, and please don't hesitate to pose questions on that. So at the moment I need to apply for final questions, please. Yes?
You haven't given the top three, so I don't know if maybe you have answered that question there, but as an obvious application field, sorry.
Yeah.
Maybe.
Switch on? Yeah.
Yeah, maybe the answer is in your third part, but I was writing yes. An obvious application to me seems to be the evaluation of EMF model. Do you know EMF model? Eclipse modeling framework models? There is an environment around Eclipse. I saw that where you draw your models and you generate code. And when you modify your model, it will regenerate the code. And what may happen is that the code that was generated, you may want to modify it by hand, making alteration to it. So they use prime mass or some kind of prime mass, so that when you regenerate it, you don't lose what you've done. But it's very, very primitive mechanism. And so very often you need to make big modifications. And when you do big modification, you lose all the instances of the code you have generated. So you understand what I'm saying? You have your model, you generate Java code, then you have instances of that code, and when you modify the model, you regenerate code, and you lose the instances. So it seems to me that you could use your system to do the migration here, because you have both models and you can... Did you think of that application domain?
No, we did not think about such an application domain before, but it is well within the formalism which is at hand. So in fact, this Eclipse model is a sort of a meta model. You may use it as a central referee for epistemological stuff. First you have to define your program, the source program, the initial program, as an ontology, having the schema for the application domain, and this is well affordable if you use model-driven software development. Then you have several revisions of those implementations according to the model, which could be treated as instances. And then you may try to transfer it either to a new release of the meta model. For example, the Eclipse model has undergone the revision yet, and you have to use the legacy stuff developed under the previous revision of the Eclipse meta model, right? So you can do that using this approach, but first you have to do some homework. You have to define the ontologies, you have to form the knowledge base, and to define the transformation between the program in a way you prefer to see it, and a knowledge-based representation of that.
Yeah, to me, ontology is the EMF model. I mean, the ontology is not.
UML has been chosen just for illustrative purposes.
Yeah,
we use an ontology web language for that. So the tool we have at the moment is for all ontologies.
Okay, so you need to transform your web model.
Yeah, it has to be extended by adding methods to process different languages. More questions?
Thank you. Sessions will be started at 12. You have coffee break at 4 hours.